Okay, guys, good morning. Good morning, everyone. So I hope yesterday's hands-ons went well, that you went already deep into your subjects. So yesterday we had the talk with Christina about osteoarthritis, and you remember she was talking about Kellgren-Lorentz scale. So as one of the metrics that they're using in order to evaluate so up to which point the disease had progressed. So today we'll have Aleksei, who will then more specifically then talk about then the analysis of these knee images in osteoarthritis, and then so the use machine learning medical image analysis in order to extract as much information as possible. So beyond the Kellgren-Lorentz grade, to assess then the disease. So Aleksei is a tenure-track professor of intelligent mechanical system at the University of OULU, and he's visiting professor at Aalto University in Finland. He has a PhD from the University of Oulu, and then he did a postdoc at K11 in Belgium and Aalto University. And in 2022, so he had his habilitation in machine learning for medical imaging. And so he's exploring, so as I said, machine learning, so to make better decisions in medical applications, so more specifically medical imaging. So he has published over 40 scientific peer-reviewed publications about machine learning in musculoskeletal disorders, cancer, dementia, ophthalmology. And so he's also participating then to a number of important international congresses and events such as MICAI, IEEE, etc. So with no further delay, Aleksei, I'll leave you talk about science.
Yeah, thank you, Jérôme. Good morning, everyone. It looks like I'm the only one who has a lot of coffee today, so I'll definitely be more energetic than you, but I hope I'll cheer you up with some of the stuff that I did in the past years. Okay, so let's try to get this whole system to work. Yeah. Okay, so this is basically where I come from. OULU is actually pretty far. So if we travel there by bicycle, it will be almost 4,000 kilometers to get there. It's in the north of Finland. We have a fairly small university, maybe actually of the size of UPF. What is kind of nice about it and why we are kind of famous, because we cycle 365 days per year. OULU is the city where Polar company got started, so it's a university professor who started Polar. Some of you may have smartwatches, some of you have Apple, but there is also Polar. Oura Ring, if you heard about that, there is a reason why it's called Oura, because it started in OULU. So founders are alumni of our university, and many people from the university work at Oura. So OULU is known also for maybe people like me, Jérôme, and Miguel Angel. We know about IRC. So OULU is a place where the IRC chat was developed. It's like a Slack that is open to everyone, and like it was before the graphical user interface was a thing. So it was like a command line thing. So yeah, there's been many interesting things happening in that area with a city that has only 200,000 people in the middle of nowhere. So my lab in particular is also doing some, I would say, unusual things for the northern Finland. So what we do is that we investigate how to build machine learning systems that reliably quantify disease stages, predict the trajectory of the disease in preclinical and clinical settings, and how those systems can also speed up clinical work and improve patient outcomes. Lately, I expanded my research portfolio to a variety of different diseases. My group is located at the hospital. We closely work with different clinicians in ophthalmology, cardiology, surgery, and different kinds of surgery as well, neurosurgery, abdominal surgery, orthopedic surgery. So there is a bunch of different people around our lab, and we help them with medical image analysis and in general, like running a large-scale analysis on different kind of cohorts. So what my group is trying to do, maybe on a bigger picture, is really assemble the puzzle of kind of technology stack that takes data from raw image data acquisition to the decisions. So what it means is that typically we have a medical image, right? But actually there is something happening before that image is formed. So I don't know if you know how the MRI works or how the CT works, but typically there is like a physical process, right? In the case of CT and X-ray, there is like X-ray radiation put through a body, then there is a detector, and then you get to observe a signal, and then from that signal you can infer what kind of tissues there are on an image. But then this process can be greatly improved. You can emit less radiation and get a good quality image. So typically, the rule of thumb is that you need more radiation to get a good quality image. But we want to have less radiation and better quality image. We want to do quality assurance. And then what happens after is that you typically try to quantify the disease in some way. So like here, you see like a multimodal biomarkers of disease. What it means is that, well, right now we have humans looking at images. Radiologists, for instance, they look at those images and they try to sort of say, okay, this person has a cancer of size 3 centimeter, or like a tumor size of 3 centimeter in like a left lobe of the brain. But of course, this type of problems can be solved by a machine. And my group is in particular doing that. We also apply this in musculoskeletal diseases, and this is the main topic of today because I've been in the past involved in MSK the most. And then, of course, once you understand the disease stage, so why do you need to even like do this kind of quantification of a process, of a biological process? Typically, you assume that there is a model, that the disease is evolving according to some law. Like in physics, for instance, we know different kinds of laws. So if we can measure empirical data and we know the model of the process, we put the data to the model, and then we can make predictions for the future. So that's exactly the same in medicine. You need to understand the model of the disease, how the things will evolve in the future. And then once you are able to capture the disease stage, then you can understand if the patient is going to survive, for instance, after a particular surgery or not. So which leads to the next stage, which is kind of the decision-making stage. And we also work in that domain. So today I'm going to give you bits and pieces from this pipeline, but in the context of osteoarthritis. So you already heard about osteoarthritis yesterday, that it's a disease causing a lot of disability. So here you can see a picture of a normal knee and knee with osteoarthritis. I would say the picture is rather incomplete because the disease also involves a lot of inflammation in the knee. So the joint, not just the knee, but also can be hip, can be hand, can be any joint, in fact. And the joint typically gets swollen, and there is a lot of other processes going on besides the cartilage damage. So yeah, the diagnosis of the disease is done with radiographic analysis. So people take an X-ray to confirm the disease. Typically, for the orthopedic surgeons, when they take an X-ray, they use it as a cutoff in addition to symptoms to decide if they kind of have the ability to operate a patient. So how the X-rays generally look like. So here's a representation of the current way we grade knee X-rays or stage the disease. What is on this image is a scale called Kellgren-Lawrence scale. What this essentially means is that, well, like in the old days when this scale was defined, people thought of osteoarthritis as a disease of cartilage. And they thought that, okay, so once you have a healthy joint and then the disease starts to appear, what starts to happen is that you start to get less and less cartilage. And then at the end, you get basically no cartilage here, and the joints, like you get the bones in the joint, they start to grind against each other, which causes a lot of pain and mechanical stress and so forth. And then during this process of losing the cartilage, the bone spurs, osteophytes, they're not very well seen in this lighting. It's a little bit too bright here, but like the bone spurs, they appear on the sides of the bones over here. So and nowadays, people think about OA in a more, I would say, comprehensive way, how the disease is really evolving. But still, X-ray is used widely for, say, studying the disease or even in clinical practice. So this is actually myself here demonstrating how to get an X-ray of the knee. Still cannot find my image, by the way. It's somewhere in the hospital archive, but I had to, I really had a hard time finding it. But essentially, this is what's happening. You go in front of a detector. So this is like an X-ray detector. There is an X-ray tube from the behind, and then just kind of the radiation hits you right there. So you can see it here schematically. And then you get an image that looks like this, so from two knees. This is not my image. So yeah, that one is mine. So yeah, then so what you can do with those images? Well, as I said, you can stage the disease, and that was basically what people did before I entered this domain. At the time when I started to work on this, people kind of explored the images only in one way, and somehow no one figured out what you need to, what you can do with them. There have been some hypotheses lying around, but the artificial intelligence wasn't at that stage where it was, let's say, in 2017. So people were not even able to look at, say, 30,000 X-ray images at the time. So the images were very underutilized. And I will talk about that later. So then another modality that I want to cover is MRI. So MRI is an interesting modality because essentially the picture you see in front of you is basically time, which is kind of wild concept to see time. Like what the MRI shows and why MRI works is that because your body consists of water, so soft tissues have specifically a lot of water. So, and the MRI can very well differentiate between soft tissues. And cartilage, meniscus, ligaments, they're all soft tissues. They're involved in the disease. There is inflammation, and you can design specific MRI sequences to measure different things in the knee. So, and this is another modality on which I spent quite a bit of time studying it. So, what are kind of the input data before my talk? We know that OA is a complex disease. It has no cure. It's very hard to model. People try to model OA in many different ways, in conventional ways, using mathematical modeling, but it just doesn't work in all cases. If the disease is biomechanical phenotype, you can model it, but somehow you take a person who has no whatsoever symptoms and they get osteoarthritis 5 years in the future, and you still don't know why. So, and there's many different phenotypes of OA, and we don't know what they are. There's now a lot of ongoing research that tells us what those can be, and we still need to spend a lot more time on that. But what interests me lately is that in OA, there's lots of comorbidities that are very deadly, like cardiovascular disease. So people who have osteoarthritis, they get to move less, and they're also generally very unhealthy. There's also many people with metabolic diseases like diabetes, so they co-occur, and people who live with multimorbidity, like 1 or 2 more chronic conditions, they are a very interesting group of patients generally to study. And I think this also has to be investigate it in a deeper way. But so far, we still don't know much. So, and I think we need better tools. So to study anything, we need better tools. When we look at cancer, for instance, the disease which has been studied quite intensively, people spend a lot of effort on actually developing tools just to study cancer. And it's in a way easier because cancer is progressing faster. But osteoarthritis is a very slow disease. It's progressing slower. So it's much harder to develop tools because the kind of a life cycle of getting feedback is very slow. So, but now we have accumulated enough data that can be used to develop tools. So I think that should speed up the way we understand osteoarthritis. So what I did in my PhD is that I specifically focused on X-rays and how can we utilize this low-cost modality to stage the disease, predict the risk of development of the disease, and even like predict how the disease would be evolving in the future. And the latter part was done with my colleagues and current students. So the main method that I utilize and my group utilizes is deep learning. So a good way to think about deep learning is that it is a machine learning technique, right? And in deep learning, we use artificial neural networks. I don't know, did you guys hear about, like machine learning before? Yeah, great. So what the idea is that we utilize the gigantic neural nets to learn some kind of useful latent representations from data. And then we can utilize those to, say, predict the risk of the disease or in a much broader context. So the good way maybe to map out the semantics is that there is AI, which is a general field. There is machine learning, which is like statistics plus algorithms. And deep learning is kind of same statistics plus algorithms, but those algorithms are combined in a non-trivial way to learn hierarchical data representations. The good way to think about like machine learning and deep learning is that you have data, right? You can write a program that extracts something from the data, and then you build a learning algorithm. But in deep learning, you just write an algorithm. So that's maybe the core difference. And why it's great? Well, it's because you don't have to spend much time on engineering the data processing, on like extracting information from data. You really focus on like basically statistics and understanding of how you can make better learning algorithms. So maybe just to remind, right, what we analyze in computers is typically, well, matrices, right? And why this whole business works in general is because data is a bunch of matrices. And a particular type of method that's been shown to be very successful in processing data of this kind of type, which is basically like a matrix with numbers, is a convolutional neural network. So what the convolution does here, it just iteratively slides over an image or a stack of images, and then it reduces the result spatially, and then it does it again and again and again until you get just a vector of numbers. And you can kind of draw an analogy to a human visual system where you can, if you look, say, at an image, you get to see like a 1 pixel, but then you kind of zoom it out a little bit, and then you see, oh, actually there is like, some kind of higher level patterns, and then higher level patterns, and then higher level patterns. What this type of algorithms are doing, they're kind of building higher and higher and higher levels of abstractions. And the interesting part is that we don't teach them how to build that level of abstraction. We actually give them a lot of data, and they will figure out how to build the level of abstraction given the objective that you let them solve. So yeah, now about the OA. So coming back to osteoarthritis, right? So coming back to this framework that I was talking about. In OA, you see the images, they kind of contain a lot of stuff. So there is 2 knees, and the images are quite big. Typical resolution of an X-ray image is 100 micron, which is like 0.5 millimeter pixel spacing. So there is a lot of kind of small details that you need to look at. And a very essential step is actually the pre-processing of those images. And maybe the first thing I want to talk about is a study called NEO. It's knee anatomical landmark localization. So this is the work where we utilized convolutional neural networks to annotate anatomical landmarks. So what this means is that we can take a knee joint and we can basically place these dots around certain areas. But these are, of course, not random dots. So the dots need to be located in the areas that are meaningful anatomically. That it should be like a center of a condyle, for instance, in the tibial bone, and then in the femoral bone. And they should also, those landmarks, they need to figure out, is it the landmark for the left knee or for the right knee? So why is this useful? Well, because if you can understand the landmarks, you can understand where the knee is on the image. You understand its orientation. So if you understand that, you can standardize the data you work with. Because those images are pretty messy, especially in clinical practice. They are rotated in somehow non-trivial way, and they're difficult to process. And another application of this is that you can actually look at the image and measure the distances. And those distances, I will show later, they can actually be used as biomarkers of disease progression. So here is an example of what this type of approach can achieve on a very, very difficult image, I would say. So we compared it to baseline. And you see, like, the problem of getting those landmarks right is actually not trivial, because there are these bone spurs, and like hitting it in the right place is very, very hard. So we developed a framework that used so-called hourglass networks. So what this method basically does is that it's a standard convolutional network that essentially, at the end of the bottleneck, predicts you the coordinates directly. But the interesting thing is that you're not like mapping the, you're just not just taking the image and then shoot the coordinates out. You first build layers of representations, and then you concatenate them together from all different levels, and then you process that concatenation forward to make the prediction. So why I'm showing this is because, well, if you want to solve problems in the medical domain, sometimes you need to build a new method. And this is a great example that, so we tried a bunch of different techniques. You can look more in the paper. We tried maybe, I think, 10 different methods at the time. And we spent quite a lot of effort on engineering this. And if you want to make something that's robust and that works, then you need to really invent new methods. But then, so once we had the block for localizing the landmarks, we were able to do automatic grading of the disease. So here is kind of a snapshot from my paper from 2018. That was a while ago. So what we did is that, then again, we tried to think of this problem in a non-standard way. So what is so non-standard about knee osteoarthritis compared to, say, general image when you try to classify it where something is a car or something is a cat? Well, if you look closely at this image, kind of the image is symmetrical in terms of the visual features that you try to look at. It's not like clearly symmetrical. The knee is not perfectly symmetrical. But the things that you want to find in an image, they are kind of symmetrical. And we simply exploited that in the neural network. The interesting thing is that as soon as we did that, the amount of parameters that we needed was many, many times less than a typical neural network would require at the time. And this method is still kind of robust. You can download it from GitHub. It's running now in one healthcare provider in Finland. They test it, and I'm going to launch it now in our hospital. Also, they got interested in this because they use KL grading for surgery decisions. So they want to utilize an automatic method right now and just stop doing manual reading. Yeah. So here's maybe the results part. We actually trained the method on something like 3,000 data from 3,000 patients, or even a little bit more. And then we validated the method on the data set of about 6,000 knees. So it's maybe like 3,000 subjects. And it seemed to be performing quite well in terms of like a confusion matrix. It didn't make any kind of stupid mistakes, didn't confuse no disease versus the end-stage disease. And the predictions were kind of quite right. And then if you look at how the method was comparing no disease versus there is a disease of any stage, then the AUC was also quite high. And then we did also an external validation in different setting. So here we looked at how the algorithm compares on data that it has never seen, data from Finland. So we trained the algorithm on large cohorts from the US. And then we compared it on Finnish data. And then we asked our own radiologists to actually grade that data and compare how it works. Well, on that out-of-domain data, we also see fairly OK results, especially the algorithm compares quite well to a board-certified radiologist. But one can see a big discrepancy around this stage of KL2. So what the KL2 is the definition of early osteoarthritis. And it's really so that if you compare also two humans together, they also have exactly the same big discrepancy, because the grading is, that particular grading system is just not good. So, well, what can we do about it? Another way to grade images is to actually, you don't like come up with a holistic representation, one number per image, but you actually grade an individual feature in an image. So what we did then was to just separately grade all osteophytes and all joint space narrowing according to so-called ORC atlas. And that worked surprisingly well, actually. So at the time, we were able to beat all state-of-the-art techniques. And we are now going to also launch this in one of the clinical experiments in the US. We put actually all our models open source. So if any of you are interested to play with this, you can download the data. It's also open. And you can download any of my models online and codes also. So, but then we thought, OK, so now we used all these cohorts from the US. They're very big. They cost millions of dollars to collect. And at that time, we thought maybe we want to kind of reduce the amount of data that we need. And we thought to work on kind of really trying to understand can we use a better machine learning method to have less data. So we focused at the time on semi-supervised learning, where we tried to use a lot of unlabeled data. So now we have been working with labeled data. So humans actually graded those, like basically thousands of knees. And how can we then maybe use data that has not been graded? So that's always a big question, because if you look at any hospital, there's data with radiology reports. Of course, now there are techniques that allow you to do, say, radiology report generation and different kinds of things. But at the time, it was like 2019 when we started to work on this, in 2018, there was nothing like this yet. So, and we thought that, OK, if we take like data from the whole hospital that has no grades, and then we take a little bit of data that's been graded by humans, can we actually learn from that unlabeled data? So we spent a lot of time focusing on developing this type of techniques where you can utilize that unlabeled data. So we published a paper called SemixUp. I will not go much into the theory of it, but maybe the most important point of it is that we found that actually you need 6 times less data to get exactly the same results. And if you are okay with losing a couple of % in performance, you actually can reduce data by a factor of 12. And in terms of like a labeling effort, that actually costs a lot of money because those images, they actually cost to grade. You need to pay a radiologist if you are, say, in an industrial setting. Yeah, so maybe I'll skip that. And also that very point in time, we pushed out an open software, which also you can download online, or anyone can download online, for grading the images. It has a UI that you can just upload the images to. It also has DICOM interface, so you can connect it to any kind of scanner, PACS. It has a REST API. You can use a Python script to push images to that. And it's Dockerized. So there's just one script. You just call one script in your Linux computer. And if you have Docker, it just starts to work. So this is an example of the UI that we've built. It's very simple. So you just choose a DICOM file, push it to the server, and it returns you this bunch of heat maps with the KL grades as a result. And we also use a technique called deep ensemble at the time to get a better calibration so that we can actually get a trustworthy set of probabilities outside of our model. So yeah, I talked about grading, but grading is kind of a one step in the pipeline, and it's not clinically useful. It's useful for the research in some setting, but it's not useful in a broader scope. So what I focused later on was a risk stratification. So when we try to look at patients and see who is going to develop the disease in the future. So that's a much more interesting case because you want to select patients for clinical trials. And since in a way you don't really know who is going to have the disease in the future, that's actually quite a relevant question. So we developed this framework for predicting progression. We also use data from the US that had something like 4.8 thousand subjects in training data, and we validated it on also on data from the US on 3,000 subjects. And the framework was multimodal, so we realized that the images are not enough. So there is a lot of data in, say, information about whether the patient had surgery before, whether the patient has symptoms, and even age and sex, they are very important predictors. So we compared the method with, at the time, kind of the best possible way to make predictions, and found that the methodology we have really exceeds the performance of conventional approaches with logistic regression. And we ran also nonlinear methods, such as gradient boosting machines and even neural nets, and it was still performing much better. And the nice part about our technique is that it actually doesn't require any human grading compared to conventional models. Typically, people collect that imaging data, they put it into a vector, and then they kind of create a set of so-called expensive covariates. The covariates that are just hard to obtain, so you need to pay someone to collect the data. So our technique is fully automatic, and it's, again, utilizable in any setting. And then we thought that, OK, so the risk stratification is important, but what is actually more important is to look at how the disease would be evolving. Because why you actually need that? Well, because you can somehow try to model the interventions. So you want to understand whether the patient will have an accelerated stage of developing the disease. You want to understand, so in addition to the risk. So the risk is just giving you basically binary value. And you want to understand also when the patient will have the disease change. The conventional way to think of it is time to event analysis, like in cancer imaging or cancer research. But we kind of looked at it in a slightly different way. So the time transformer methods were kind of a thing. And we thought that, well, we can actually treat the problem of predicting disease progression as like a translation problem. So in translation, you take a sentence, and then you kind of read the sentence, and which is a sequence of words, and then you predict a sequence of other words. And those transformer methods, they were really, really good at, and they are still very good, state-of-the-art techniques at predicting sequences. And we also thought that maybe, since we have those new methods, we could do something even wilder. Instead of just throwing all data at once to the model, we could do like a proper multimodal data fusion, the same way it's done in a clinical setup. So we got inspired by a decision-making setting, where typically a general practitioner who actually tells whether the patient is going to, say, go for to see a surgeon or going to, need some kind of special treatment, that doctor requests a radiology report from a radiologist. And we tried to model that in our framework. So as I said, we utilize the technique called transformers. Maybe I'll not go too much into the way how they work. You can read the paper that's called "Attention is All You Need." It's a kind of a very catchy title. I believe it's been cited maybe more than 15,000 times since 2017. It's quite an impactful paper. And what's nice about it is that, as I said, it can take a sequence as input, and it can spit out the sequence as output. So, and then there was another paper that looked at how we can represent images as sequences. So if you have an image, you can kind of cut it into pieces and then read it one by one, and then it's basically a sequence. And well, we thought, well, why can't we do it also in our case? And we apply this in our framework that's called Climate, which is an abbreviation for a very, very long title. Published a couple of papers on this. But what this framework allows to do is to take any kind of data as input. You can take scalar imaging data, 2D imaging data, 3D imaging data, represent that whole thing as a sequence, and then use our decision-making framework where we would have a kind of a radiologist network and a general practitioner network to kind of make the final prediction. So maybe to illustrate this a little bit more, so we can basically take any image and represent it as a sequence of vectors. Sequence can come from directly from an image if you slice the image into patches. You can also use a convolutional network that will produce you essentially like so-called a feature map that you can unroll into a sequence of vectors. And then once you have a sequence, well, you can concatenate with it with any other sequence. And that way you can fuse data from different modalities together. And then what transformer does also, it takes sequences input and it produces sequences output. So what this implies for us, for people who develop the models, that you can actually then develop a fusion model. So you can basically process the data with one network. Then you can process the data with another network, also sequential data. You can put those two sequences together and then put it into another transformer. So if everything is a sequence, you have this universal computing machine that can process any data, and which is super cool, I think. And you see like the advances like ChatGPT, they are powered by these kind of models. They are powered by transformers. So we validated this technique in 2 domains, in osteoarthritis and also in Alzheimer's disease. I'll not go into details of the validation, but we had data from quite a few subjects many different time points when we tried to predict how the disease would evolve in time. And there was extensive data selection and many other technical details. Long story short is that if you take our method, it performs better than any other technique that existed before, including the transformers. So it's not just the transformer that makes a difference, but the way you utilize it. And I think this also is demonstrated now by, say, in general AI field, where you have things like ChatGPT. The GPT technology existed already in 2018, 2019, but ChatGPT came out after 2020. So what made the revolutionary impact is that you utilize this model in some kind of different new way. And we also observe this in medical field. So if you can utilize a method in some kind of a new way, then it can make a very interesting impact. But I talked a lot about the X-rays, but I didn't talk much about the MRIs. So in MRIs, we focused quite a lot on segmentation. So segmentation basically allows you to delineate tissues in medical images. So here's a setup that we had for several papers. We also had data from the US and 2 internal data sets from Finland. So the US data was actually a little bit less in terms of size than the Finnish data. So we focused at that time quite a bit on domain adaptation because we didn't kind of have the Finnish data yet, but we thought, okay, once we have the model trained on the US data, we want to run it on Finnish data. Would it work well? So it turns out that it doesn't work well. So why? Well, because there is a domain shift. So what you see here, maybe this is the most representative plot, is that you have a baseline technique, just a general UNet. So UNet at the time, I guess I'm telling more like a history lesson here. 2019, 2020, it was still like a state-of-the-art framework to segment medical images. And the baseline technique was always underperforming when you move to the new domain. So if you move from country to country, you automatically get worse performance, even though the imaging parameters are very much the same. So there is lots of other details, of course, in the way the images are acquired. But we thought that, well, that shouldn't be the case because the images are the same. But somehow, some small parameters, small nuances, they are different. So we developed a methodology called domain adaptation that helped us to actually generalize from one domain to another domain. So yeah, and we did also an extensive set of validation trying to look at how the method performs in different stages of the disease. Because, of course, on healthy knees, everything performs kind of well. But when the patient has already a KL4, the final stage of the disease, then you don't get a very good performance. And you observe this kind of performance drop even more if you have a domain shift. But then we said, well, fine, we can segment, but what next? Similarly to the knee X-ray, in MRI, you also want to do tissue quantification. And there are, of course, holistic grades that you can assign to images, but they are quite complicated, noisy, and there is not enough data. So the conventional approach is to actually take a segmentation and then label it according to a multi-atlas, and then extract the quantitative parameters within the MR segmentation. So we implemented a couple of atlases that existed manually in our framework, and were able to fully automatically segment the images exactly as they are in the literature. But then the question is, how do we validate that this is good? So what we did is one step further, where we tried to look at whether we can use our segmentation model to make the same conclusions from a clinical study. So we had the manual segmentations and manual thickness measurements and volume measurements from cartilage and menisci. And we tried to look at whether we get the same odds ratio. So interestingly, we odds ratio like to predict progression, like it's a pain progression or structural progression, different kind of progression. And what we found is that we get different odds ratio in terms of numerical values, but the conclusions we get are actually quite the same. So we don't have the exact ground truth because the other method is semi-automatic or semi-manual. So there is a lot of, and it's unclear how it's really done. But what we see is that we get about the same conclusions from both methods. And the biggest difference is that our method you can just download online. And you don't need to, again, pay a consultant to use it. But then those segmentation masks are used for something, right? Those thickness values are used for something. And what they're used for is to, again, stratify the risk of patients, because then you can find the patients for clinical trials. And we thought, well, OK, if we can do segmentation, maybe we can apply the same framework we did for the knee X-rays. And we can somehow incorporate a large volumetric medical image into the model to make prediction whether the patient will have an increase in the current severity of osteoarthritis. And yeah, so we did a technical paper at ISB where we tried to look at how we can do it, basically. Because the typical question is, OK, you have a 3D stack, which is like 160 by 160 by 160 pixels. So it's a lot of data. It's very hard to train a neural network on this kind of data. And the typical desire that occurs among researchers is that how about we do not process the 3D data, but we process 2.5D data, where we just read the image slice by slice. And that's what we were basically kind of investigating. What we found is that you can actually do slice by slice reading in this particular problem, and it works really well. So this inspired us then to say, well, there is different kinds of MRIs we have in osteoarthritis. And how about we take X-ray and all MRI sequences that exist and train like a gigantic neural network that would be able to predict whether the patient will have a disease severity increase or not. So very interesting results we found is that, well, not all MRIs are equal. And you need only actually a few sequences. And in many cases, X-ray is actually quite good. So if you try to predict longitudinal progression, say more than 12 months, then just use X-ray. You will get fairly same conclusions. If your goal is to look at the disease in short term, that's where the MRI is useful. But otherwise, in different subgroups, including like injury, different disease stages, we observed that X-ray is just good enough. And the cost is just uncomparable. The cost is like maybe 10 times different when you run a clinical study. But so far, I showed a lot of things on data that has been collected. And while it's kind of cool that we had a lot of interesting stuff developed, the main conclusion is that I think we reached the limit with existing data. There is simply not any more data in research that's been collected that we can make further progress. So I call this we need to somehow discover the physics of osteoarthritis. So we need to figure out the disease models. How do we do that? Well, I think we need different kinds of data. But data collection is expensive. And I don't think that there is any way to collect data like we had before. And we need then maybe look at the techniques that can be used to collect data. So here, my team has been developing now a method for adaptive experimental design, where our goal was to actually build a machine learning method that collects data. So it tells you basically when a patient is likely to have a disease progression event, like a change in the disease severity. And if that's going to happen, let's say in 24 months, so that's exactly the point where you need to measure that particular patient. You shouldn't measure the patient in a cohort every 12 months because it's a lot of resources. So that way you can actually save quite a lot of money when you construct the cohort. So here the way we analyze the data, we look at the progression in terms of radiography. We looked at joint space width, like quantify joint space width. Well, one way to measure it is, for instance, with the Neal method that I introduced in the very beginning. And there is a particular definition of what people qualify as a progression in joint space width. So if the joint space width has decreased by 0.5 millimeters, like 5 pixels basically in an image, then it's a progression event. So that number, the threshold, already incorporates the noise that you get in between acquisitions. But So if you try to collect data, so we need to think of it in a different way, not the way we typically think about machine learning. So many people think about machine learning is that, OK, you have some data, right? You put a piece of data in, and then you make a prediction. And the prediction could be like yes, no, like predict disease, no disease, or what stage of the disease, or even like a trajectory of events, right? But here we are really talking about decision-making problem. Why? Well, if you start in the very beginning for a patient to collect data, if you make a decision to collect data, then actually this whole tree of possibilities is expanding quite rapidly. If you follow up a patient for, say, 8 follow-ups, that tree will be already very big. So here's, for instance, the case for 3 follow-ups. So you can see, like, we follow up a patient in 12 months, and there is 2 possible events. Patient will have a progression or no progression. But if you follow up in 24 months, there is actually much more events, right? And you need to take into account all of those possibilities if you want to make good predictions, because they have financial impact. So the way to solve the kind of decision-making problems is with reinforcement learning. I don't know if any of you heard about AlphaGo. Like it's a computer program that is able to play Go, the game of Go. It's basically like, I would say, Asian chess, so to say. But the Go is much more sophisticated than chess. It has essentially like a crazy number of all possible combinations that you need to analyze if you want to make good decisions, if you want to win someone. And it was thought to be an impossible problem for a computer, because, as I said, the number of all possible situations is just crazily expensive to analyze, and we don't have computers that can do that. Well, it turns out that if you use neural networks that do not like explicitly enumerate all possible possibilities, but just predict what is likely the next step, what is the next best possible move, and you take that network and you make it kind of play with itself. So the self-play is an important component, it kind of trains itself. That turned out to be quite a useful strategy. And so, yeah, so people trained this type of system using a reinforcement learning framework. In a nutshell, what reinforcement learning does is that it helps you to train an agent that interacts with an environment. So the environment here, it reveals you a state. For instance, here you get the field of the game, and then you make a move, and then the environment gives you a reward. Could be positive or negative reward. In some cases, the rewards are delayed, so you don't get to observe them immediately. You can get to observe them only, after you finish the game. Yeah, so and that's how it works in a nutshell. And there's a bunch of different techniques to train those methods. So we thought of the problem of data collection as a reinforcement learning game. So we said, well, if we basically have the following path, that you start at the baseline, and then your goal is to decide whether to visit next time or skip. That's the only kind of decision you make. And then you give a reward if the patient has actually progressed, because we have the data, so we can train the model using the retrospective data, because we know who progressed and who did not progress in those large cohorts. So, and that actually turned out to be very nicely framed in a Q network setup. So Q network is basically a setup which tells you, OK, you get to see a state that the environment reveals to you, and then it allows you to tell which action has more value. And that value of an action, it is kind of, it's not in the equations here, but that value function that kind of tells how good the action is, it really takes into account of all possible future events. It's not accurate the way it works in reinforcement learning, but if you train the model for long enough, it learns to interpolate between the things that are actually good. And so you don't need to know all possible events. You just need to know enough events so that you can make kind of a hunch-based decision like humans do. We don't know everything when we make our decisions. It's just we recognize patterns well. And then if we recognize patterns well, we can make good decisions. So here what we did is that we took 2 images from a patient, extracted the probabilities of the KL grades using the framework that we developed before. We fused that with some clinical data. And then the network was just telling us whether to visit next time or skip. How do we make network be aware of the time? Well, that's an interesting, I would say, trick. So here we just kept the index of the latest data collection time, and then we basically put a current index. So network implicitly learned the disease progression model, which we didn't kind of teach it to learn disease progression model, but it learned that. So there is quite a lot of technical details on actually how to make it work, because the biggest challenge in this framework is that, okay, you basically try to predict, like you try to be as accurate as possible in detecting whether the patient will have a progression. But at the same time, you try to save money. So accuracy and money, they are not in the same units. So you cannot add those 2 things together. You need to convert accuracy or like the outcome that you care about into financial units. And this is what we did. So we applied the knowledge of health economics that was through which we found like kind of a rough approximation of how much 1 millimeter of joint space width loss would cost. And based on our analysis, we just say, okay, well, the simplest possible thing you can do, you take the total knee replacement cost, the surgery that you get at the end, and then you divide it by the mean joint space width of all healthy knees in your cohort. Sounds like a very rough idea. Someone would criticize me for that. But based on our results, it turned out to be quite a good idea, actually. So without maybe further details, so here's the reward function. Essentially, so what the reward function is what the environment that trains an agent kind of returns. So here, a bunch of different mathematical terms. I will not explain them in very detail. I will just tell that after playing with the formulas for long enough, we were able to combine accuracy and financial units together, and accuracy specifically in joint space width loss terms. Yeah, so here are the results, and the results are maybe they're quite busy here, but we will look only at one column here. So the reward function itself is a good metric. So here's the result of the test set. If your method is good, on average, it needs to give you a positive reward. So, and our reward was designed exactly that way. So if you take a bunch of existing baselines, including our own methods that we have developed, well, it turns out that even our own methods were working kind of quite well, but they were not better than, say, a tool that you can download from GitHub. So there's been better methods that were not domain specific. You can just run them, and they work really well. But only our reinforcement learning based method, because it was optimizing the same objective as we, of course, evaluated it on, it was able to get us good results. Also, in terms of other metrics, like the on average, whether we can get a good accuracy and good recall. So recall is a score that reflects on how many positive events or like progression events you can capture in our case. Our method yielded the highest performance among all the baseline methods. What's interesting about this particular study is that we did not just look at the knee level. So I think one of the problems in OA research generally that people look at only one knee. I think this is a mistake. And now we see studies where people try to combine 2 knees together to make predictions. So well, we also did that. And it turns out that if you take any method, even the one we had before, and then you validate like at the patient level or knee level, of course, patient level method, when you try to predict progression, it works much better. And reinforcement learning method works even better. What's interesting about this is that these metrics, like balanced accuracy and recall score, this is not something our method was optimized to solve. It was really optimized to solve that reward function that has a lot of mathematical complexities. And once you run it in the more conventional machine learning metrics, you get that it actually does beat the baseline in different settings. Then we looked also at the way the policy that we trained behaves based on the disease severity. So what we did is that we took 2 KL grades from a patient. We put them into a tuple here and just kind of sorted them. So we see that so lambda here, it states the data acquisition cost. It's normalized in US dollars, so it's about like $500 per acquisition. We see that naturally, when the acquisition cost is fairly low, the method tells us, well, you need to follow up more. And if the acquisition cost is very high, it's kind of quite conservative in the way it behaves. Very interesting that the method kind of implicitly discovered that, well, if you have a KL4, you need to, patients who have the KL4, at least in one knee, you need to follow up them regularly because they progress. And we didn't teach the method to do it, but it discovered to do it so, just from the data. And that was interesting. It means that the reward function is really, really good, that it really aligns with this metric that we would kind of naturally put there. So maybe kind of to give a wider perspective of what I now think, that OK, we have a lot of different techniques that me and my collaborators and students have developed. But then I think we still are quite far from getting the drugs for diseases like osteoarthritis. What I think is really the important problem is that people who got OA, they are just basically starting to get really sick. So you see, like, there's lots of people who get stroke. If you have an osteoarthritis of a certain severity, you have 30% higher risk of stroke. If you have been diagnosed with OA, your risk of cancer is increasing in time compared to people who have not been diagnosed with OA. So we need to pay closer attention to those people, and I think this is really the next big thing in the OA research. And like now, I have some projects on that domain, so which I will briefly introduce. So just an announcement: I'm hiring. I am hiring one PhD student that would focus exactly on this problem. We have a wider scope of projects that focus on opportunistic disease screening. So what this means is that we exactly take data from patients who already store data in the hospital. And then we analyze the data for, say, future risk of stroke, future risk of cancer. And we try to look, maybe they already have cancer. So this is quite an interesting cohort of patients because they get chronically ill. They may already have a chronic condition. And people with multimorbidity are generally prone to other more deadly conditions. And that's what I'm looking at right now. So in summary, just to conclude that OA is a disease that has no cure, and it's very hard to actually find a cure. I think AI is one block in this puzzle. And we need to also focus a lot on building tools for preclinical research. So the tools that I have shown, they are working for the case of clinical research. But for the laboratory, we still need to bring new tools, believe me or not. But in many labs that focus on drug development, people still use manual segmentation, and which is kind of ridiculous because automatic segmentation is around for 10 years. And I think that, yeah, so what AI can do in the field of osteoarthritis is improve the acceleration of imaging, which I didn't talk about, but this is something we work on right now. So things like MRI reconstruction is what one PhD student in the group is working on. Large-scale data analysis, so I showed things that would allow to quantify MRI scans, and tools that help us to do data collection. And yeah, so I think that people with OA need to be paid close attention to, because this is where I think we start to get a lot of information. They start to visit healthcare centers, and that data is not utilized at all. So more opportunistic approach to finding what those patients will develop and analyze which patients with OA have what comorbidity risk at what stage is needed, and that's currently not a solved problem. Finally, I'd like to thank my group. One of my group members is here, Snash over there, who is working on spine and part of Disc for All Consortium. Yeah, I don't have a big group, which I intentionally keep small nowadays. So yeah, because of these people, all of that research is possible. That's about it.
Thank you, Aleksei. That's impressive talk. Super cool. Questions?
Thank you. Nice talk. I have probably a very fundamental question that I just didn't catch quite well. In the climate method, what do you need to split the image in sub-images? I mean, you can use as a sub-image an entire image, can you?
Yeah, so let's go into the technical business. Maybe I'll show. So this is kind of, right? So one way to split an image is through a vision transformer approach, where you take an image and then you cut it into pieces. You concatenate it into a sequence, and then you train a model that would learn how every patch or how every item in a sequence, or they call it token, can attend to every other token. So that's one way. What we did was basically kind of an exploitation of things that the convolutional network can do. So if you see what the ConvNet is doing, right, it takes, there is a convolutional layer, right? So you do convolution, batch normalization, ReLU, then you do max pooling, and then you repeat it for many times. So at the end, you get, like, for an image of size 256 by 256, you get like a feature map of 7 by 7. So what we did, we actually unrolled that feature map into a vector of 49 superpixels, of 49 tokens, but then those tokens had a dimension of 1,000 because of the feature map size. So there's like 1,000 feature maps, and you can unroll them into a sequence. Yeah, that's what we did.
Okay. Yeah, thank you. And then I have a more philosophical question, which I'm a bit scared to ask because, but you showed that when you compare your algorithm to radiologists, right? You said when a radiologist is sure about what he sees, then the algorithm is also sure, and that's always good. But then when the disease is not yet in a stage that, you know, there is a lot of uncertainty from the human, also, I mean, the machine result and the correlation, whatever, the fidelity of the algorithm, and then you say, what can we do about it? And then I was thinking, but this is like philosophical, as I said. Can this kind of approaches, of course, with the proper modification, be used for generating images that the algorithm has already graded to train clinicians to actually give the same answer that the algorithm would give? Because, I mean, if we are in an obscure world where the radiologist is just as bad as, as whatever, coin, I mean, it's, why don't we teach with the machine the clinician? That's just philosophical.
Yeah.
Do you think it could be a feasible idea?
Yeah, so interesting that like a couple of days ago, I will give you a philosophical answer and philosophical question. So a couple of days ago, I watched a YouTube video. This YouTube channel called Veritasium. It's a person who has PhD in physics and education, kind of legit YouTube channel, I would say, with proper information. He explored one interesting topic, what it takes to be an expert. And research says that in order to be an expert, you need to spend a lot of time. But one of the biggest things is actually you need to get feedback. So the problem with radiology is that they don't get feedback. They get feedback from fellow colleagues that, OK, this image is graded correctly or not correctly. But actually, the feedback that they need is that, like, do they kill people by not detecting cancer, for instance? And it's a really long way to get this feedback, so you need to spend a lot of years training in radiology. So answering to your question directly, people are looking at how you can use AI to actually teach medical doctors better. Because, yeah, if you can teach someone to drive in auto simulator, you don't need to have like 50 car crashes to learn to drive. So I think we can do something like that in medicine too. And when it comes to this particular result, right, I think that the grading system itself is kind of flawed. So the ORSI grading is a much more reliable system when it comes to X-ray, and generally X-ray is an incomplete modality. It's good for something, but it's not good for everything. So you can use X-ray to decide if you need MRI, for instance. So there is like, it's not an answer to the disease, it's just one tool. So I think we need better ways to actually find new types of grading systems, even for X-ray. And that's something that people have been trying to do for a while, but so far without success. I would say that this type of stuff where you grade individual feature is useful, but then it's very hard to utilize 6 individual grades in your analysis, because you get 6 numbers, and humans are not good at perceiving more than one number when it comes to saying that you have a certain disease stage. Well, you cannot think 6-dimensionally. So yeah, there's a lot of work to do in this.
Thank you. So, but just before I hand the mic to Carrie, because voilà. It's a bit related then to that. So why sticking to Kellgren Lawrence? I mean, I understand this is what
there's nothing better.
This is what medical doctors are using, no?
Yeah.
But what would you like then to have an intelligent image analysis results? Then keep sticking to the Kellgren Lawrence. So would it be impossible then to say no, this is a new grade, so this is given by machine learning, that is much more robust, and then train medical doctors to start then to work with this new grade?
Yeah, that's what we are now kind of trying to conceptualize in the lab. So you have these 6 numbers, right? Essentially, these 6 numbers are actually good. They really tell what's going on. But this one number that you get, the KL grade, is kind of, it also comes from an obsolete, I think the paper got published in like 1950 something. No one here actually even was alive at that point, or even in a project. So it's really old paper, and osteoarthritis at that time was even called osteoarthrosis. So it was a different disease. So the grading system is obsolete. But so far, we haven't come up with ways to look at 6-dimensional structures in an efficient way. And I think in the future, there will be techniques that would allow you to say, if you can grade features individually or identify that, OK, this is this and this is that in an image, then you could somehow learn what is the grading system naturally kind of, because the grading system needs to reflect the disease stage. Why we have staging? Well, it's the same as in cancer. If you know the size of the tumor, you know how the tumor is going to be progressing, because there is a diffusion equation, let's say in brain cancer. In osteoarthritis, we also try to have something like that. Right? If we know the stage, we could predict how things are going. But we are bad at understanding six-dimensional entities.
Hi, good morning. So myself, Dr. Chiranjeevi. So thanks for the nice talk. So after this talk, I feel like nothing left to do. So on this particular topic, on this topic, especially in machine learning and deep learning. So as you've done so much of work on this, so my question is a little bit. I have so many questions actually. My first question is on. So you used a USA dataset, no?
Pardon?
United States dataset.
Yeah, it was 2 datasets, OAI and MOST, yes.
Okay. So we are about to get NFBC dataset from OULU.
Yeah.
So why not use that?
Well, at that time, it didn't have knee data, right? And still, I'm not aware of the situation with the knee data. I think someone is now trying to collect it, but it's a kind of ongoing project. And we are involved in different projects with the person who is collecting that data. But I'm not kind of actively monitoring because once there is sufficient amount of data, then we will look at it. So far, it's still kind of a data collection issue. My group now is interested in opportunistic screening, where we really try to look at what are the comorbidities and multimorbidity patterns in people with OA, and then what is kind of the grading system in OA, because we need that. Otherwise, this is not going anywhere because we use some kind of a noisy feedback all the time. KL2, not KL2, it's unclear. And sometimes you see people who have been living very healthy life. They are over 60, they have joint space narrowing, and then no osteophytes. So they don't fit in any category in Kellgren-Lorentz system, which is kind of ridiculous. So I think there is a lot of work in that domain, to be honest. And frankly, I think nowadays, if one wants to make an impact, one has to develop tools, because tools is really what makes a difference.
Okay. So is it a public or private?
Pardon?
Public or private dataset?
What dataset?
Like it's a open source dataset.
Well, the OAI and most datasets, they are open, yeah. As OAI, you can get with any university email. And most dataset, study PI needs to apply to National Institute of Aging. And the tools that I presented today, you can download them from GitHub from my group.
So it's most of your work is on segmentation or semantic segmentation?
Well, semantic segmentation is segmentation, right? So segmentation is one thing that we do, but in different domains, of course, also outside of OA.
So semantic segmentation means it's like a class-wise, pixel-wise classification, whereas segmentation is like a group-wise, so much difference is there.
Yeah, so semantic segmentation means that you indeed classify pixels in 2, 3, whatever, n categories, right? Segmentation broadly includes semantic segmentation, instance segmentation, panoptic segmentation. So there's different kinds of segmentations.
So can you go back to your slides?
Yes. Which? On the segmentation?
Yes, no.
This one?
Go back like 18th slide.
Here?
18.
18.
1.8.
1.8. That's, yeah.
Yes, here. So the architecture is like a unit model.
It is like a unit model, but it's not quite like a unit model. So it doesn't really do an aggressive upsampling step, right? And what it does is that it just builds a rough feature map. So it learns basically like a heat map of every landmark. And then there is a soft argmax layer that predicts the landmark from a heat map.
Okay. So you started with X-ray images and then moved on to the MRI scans.
Pardon?
You started with X-ray images first, then you moved on to the MRI scans.
Well, we do several lines of work at the same time, so it's not one thing that we do, all right? And as I said, OA is just one thing that we've been doing, but now I have projects in ophthalmology, brain cancer, different kinds of abdominal cancers.
So with my knowledge, what I understood is MRI scans itself is a time sequence data sets. Time sequence.
MRIs.
Depends, yes.
Yeah.
Then why to go with you showed some time sequence data set, getting a time sequence data set.
I'm not sure I understand the question.
Yes.
Progression of the patients was X-rays.
Yes.
Yeah.
So why to go with that? Why don't you use directly MRI scans?
Well, because MRI scan costs 6 times more than an X-ray, right? If you want to predict a progression, well, we found that if you look at, say, the value of MRI, like what's really the value of MRI? And it's been confirmed by many studies already that so what these scores are is the AUC scores and average precision scores. And then we observe, so these are different modalities that is in the top corner. So F8 is the fusion model type 8. You can read it in our paper online. And the orange line is X, so it's X-ray. And then we look at different, so to say, different time points. So what happens in 12 months, 48 months, 96 months. So we found that X-ray is actually not that much worse than MRI, but it allows you to keep 6 times more budget. So maybe if you are to launch a study on OA, you would rather keep an X-ray, and if your goal is to see how things develop longitudinally, it really gives you an informed decision that you don't need to spend money on a lot of MRs, but you can actually get more patients, which gives you higher statistical power.
Thank you.
Thanks. So actually, you mentioned the data. You say segmentation is around since decades.
Yeah,
and
10 years.
And there's a lot of data that are not being used. Actually, that's a very important point. So we're working with the hospitals. A lot of data are not being used because there is a huge, massive work to do for the proper annotation, for the proper accessibility of the data. And data have been accumulating over years without having that work of proper data annotation done. So now it's a massive work. It's like you stop tidying up your home during 1 year, and then you will have to spend a couple of months in order to get things right. So this is a bit what is happening very often in hospitals, and radiology services cannot really dedicate the time of the radiologists to do that work. So then luckily, thanks to this kind of research and then the outcome, so that gives the motivation to the hospitals, not only to the hospitals, but also to the different policy regulatory agencies. So in order to promote actually then a better curation of the data, better accessibility of the data. And so here, for example, in the Catalan health systems, so we have a good example where an effort is made then to collect all the data from the health public systems, so that are obviously then anonymized and then reshared for research. So it's not totally there yet, but that's on the way, and I think this is what will eventually then really empower this kind of the transfer of this kind of research.
Interesting story about the data in this paper in particular. So when I started this specific work, the data didn't exist. So my advice to young people always, if you don't have data, then learn how to annotate data and sit down and annotate it. Data annotation is something you can do. And you don't have to be a radiologist. There is nothing secret in placing these dots, and you read a couple of pages about anatomy and see how the X-ray image works. Ask a clinician to recheck and get maybe a clinician with do a study with yourself, and then you have the data set that didn't exist. And instead of asking radiologists to help, you can do it yourself. And sometimes I think it's a problem in computer science generally that people are afraid doing the dirty work, that's really getting your hands dirty with data annotation. But I think if you haven't annotated the data, you're not a data scientist.
More biomedical engineers needed in the hospital, I think. So we're already 5 minutes beyond time for the coffee break. So I think that we can leave the discussion here. Maybe there are two questions you can ask yourself, as whether all that stuff can work with little data, small data, which is most of the reality in the hospital and of the cohorts. And then, so how would that be eventually then correlate with symptomatology? Yesterday, remember that Christina was saying that Kellgren and Lawrence or image biomarkers were not already correlating with symptomatology. But why do you treat a patient? You treat a patient because the person is in pain, not because, ooh, you have a terrible medical image. You're well, no, but I will treat you because you have a terrible medical image. This is not how it works. So this is, I think, we can leave these two questions. You can catch up with Aleksei, and let's have a coffee. And then we'll talk about the data with Francis.